Preserving image properties through initializations in diffusion models. This is work by Jeffrey Zhang, Xiaoyu Chang, Caden Lee, and David Forsyth. We observe that training diffusion-based methods like Stable Diffusion fail to consistently generate images with specific distribution traits. For example, our dataset consists of fashion images that feature a white background, centralized products, not cropped garments, or models standing in similar poses depicted from head to toe with cropped faces. When we train Stable Diffusion on our dataset and evaluate the results, we see rather than getting generated images that behave like our training images, we get results that might be a zoomed-in picture, but it's hard to decipher which part of the garment or model it's actually zoomed in on. It's clear, though, we are unable to preserve the features of our dataset. This discrepancy lies in the initializations. Test time initializations are not the same as training initializations. State-of-the-art models see a blend between an image and noise during training, and at test time, it's actually initialized with pure noise, because they assume that alpha t is very small. However, a blend between an image and noise is different from pure noise because the spatial averages are noticeably different. One way to control this might be to make this blend very, very small. Giving this a try, we see while reducing alpha t during training does offer some improvements, the generated images still fall short of expectations. The resulting images are underexposed, the models are not positioned correctly, and the backgrounds still appear to be noisy. Furthermore, training with smaller alpha often makes learning much harder. Our method solves this issue by using initializations during test time similar to those used during training. The early stages of training include the ground truth image with significant noise added. But if you look closely at the noisy image, you can almost see a ghost of a garment in the image. That's because the spatial averages of a blend between an image and noise are not the same as noise, and we want to preserve this property. So we want our initializations to have a ghost of a garment in it. Consequently, we can approximate this image here using simple mixture models such as PCA to generate initializations that mirror this. We can focus on PCA 0, the class mean of garments, because it's the most straightforward and generalizable between examples. We add noise to this image to resemble the initialization during training. We call this inference method PCA-K offset inference, but in its most basic form, PCA 0, it equates to the class mean. Using the class mean and adding noise to the image is what we refer to as our mean offset inference method. Notice, instead of using pure noise as the initialization, we use the class mean plus noise and run inference as usual. Here, we depict using the class mean for garments, but we can also use the class mean for models for more accurate generation. Our mean offset inference method yields significantly better results when applied with standard training procedures. In fact, it successfully captures nearly all the features of our distribution. If we zoom in for more detail, notice that state-of-the-art does not describe the white background text. It is cropped, not centered, and frankly, not showing enough green patches. If we look at most of the examples, all desired features are captured. However, it is important to note that some images, like this skirt, also have issues. Despite saying no person in white background, we clearly see that a person is wearing the skirt and the background is not white. This discrepancy is due to potential mismatches with the true initialization during training and our approximation. To address this issue, we implement the same initialization from mean offset inference, in the training procedure to prevent any mismatches between the initializations. We apply this change to the initial time steps, ensuring that the initialization process is consistent during training and inference. Refer to the paper on how many time steps to use. We refer to this method as mean offset training. The time steps afterwards are trained using normal DDIM procedures. With this modification, we can maintain all the desired features from the training distribution while significantly enhancing text guidance. We don't claim to generate everything perfectly according to the text, but our skirt no longer has a person wearing it, and other images are reflecting the text quite accurately. As we've seen, there are qualitative improvements, but it's easy to be confused by qualitative data. We can verify this quantitatively by showing the clip similarity between the text condition and the images generated, and observe that the mean offset training plus inference is closest to the clip similarity of the ground truth garments. We further analyze the intermediate diffusion time steps to reveal that the first prediction made during inference profoundly impacts the entire generation process. You will notice that the image predicted during the initial time steps largely determines the appearance of the iterations that follow. Our method succeeds in generating a prediction from the first iteration that is very similar to our training distribution, resulting in a final generation that meets our requirements. In conclusion, we show great results by carefully controlling the conditions between train and test. We believe our approximate initialization distribution has a wide range of applications, not just confined to fashion retail images. Scenarios where images adhere to certain structural requirements could particularly benefit from our training and inference procedure. Furthermore, we recognize not all distributions possess images as structured as those in our dataset, permitting class means for initialization. Going forward, we plan to explore building better associations between PCA-K initializations and text features, as well as exploring richer initial distributions for better generation control. Thank you.